We'll start presentations a week from Monday. This Monday is a holiday. This next Monday is a holiday, right? For Columbus Day. But this is the schedule that Jerry put together as of yesterday afternoon. This should be what's on Stellar. People want a copy? She made copies. Here, you can pass them around. If you don't want them, leave them in the back for scrap paper. Anybody have any questions on the presentations? You've had fewer questions. Maybe the word's getting around. You only have 10 minutes, but any topic you want. Hopefully you will pick something. Well, actually, you can pick anything you want. Some people have done cooking because they like to cook. There's a lot of material science of cooking. In fact, Dr. Taylor, who works with me, is thinking about doing an IAP course on the material science of bread. Okay, and we'll have to get ourselves some little ovens and some mixers, and so there'll be a lab component to this, and you can eat what you cook, which may or may not be good. In any case, next week on Tuesday, I will lecture and finish up for my part, and on Wednesday, Professor Slocum, who has apologized because he thought class was at 10 o'clock. He actually was sitting in his office that day, but there was a miscommunication. Anyway, he's going to come in and talk about his combined pumped water and desalinization idea, where in certain parts of the world where you have an ocean next to a mountain, you could do pumped water storage on the side of a mountain, and then you could have the high pressure of the water go through a reverse osmosis process, and you basically get both desalinization, good or low salt water for use for a population, and you could easily do things for a couple of million. He's a couple of million people. And he's looked at the different areas of the world that this can occur, and he's done some of the engineering analysis. It's just a new proposal, and he just came up with it this summer. So it's a complex problem, and it's a way to make the whole process of energy conversion and water desalinization, sort of combine them for tremendous energy and cost savings. So it's a complex engineering system, a new type of design that he'd like to talk about. I wanted him to come in because I consider him one of the three brightest people I've ever met. All of whom that I met have been from MIT. There's another person that I would have included and did include for years in my top four, and he was Chief Technology Officer at United Technologies. And then we got into a debate once as part of a committee. It wasn't actually me getting into debate. I said something and someone else agreed with me. Actually, what I said is there's only three things that increase the wealth in the world. And I said it's mining, agriculture, and manufacturing. Everything else is just redistribution of the wealth, if you start thinking about it. You go to the dentist, okay? They're not producing anything new in terms of material goods or anything. They might be improving your health, but you're sort of redistributing the money. Financial people on Wall Street, what did they ever produce? Except depressions, okay? They're just shifting paper around. Anyway, another person, a research fellow at Intel, argued with me that I should add knowledge as a fourth area. But mining, which means oil business or coal or getting ores out of the ground, you're getting something that can be made into something. Agriculture, you're growing something that's useful, food, and manufacturing, you're taking things and putting them together and adding a lot of value. And all those things increase wealth, whereas, religious clergy, doctors, lawyers, most of these people are just teachers, just sort of redistributing the wealth, right? And it's not always redistributed very fairly either. Anyway, so we get in a big argument. To him, wealth was money, okay? He couldn't see a broader vision of wealth, so I took him off my list of smartest people. But he was someone who was very thoughtful. One of the only people I've ever talked to where I had a hard time just in a casual conversation keeping up. And it wasn't that he was incoherent. He was about 3 steps ahead of wherever we were in the conversation. And it was hard to track his conversation. He's a brilliant guy. He was on the board of directors at Draper Labs and other things. But I just couldn't figure out why he couldn't. He could only define wealth as money. But a lot of people define success as how much money you make, right? And that's not true, okay? It might be for some people, but I'm not. If I wanted to make a lot of money, I'd become a financial analyst on Wall Street and steal it from everybody, okay? Anyway, that's what they do. And there are actually now people, Bernanke, actually, the head of the Federal Reserve, he just came out, I don't know if people saw it a week ago, he actually said, yeah, there should have been some criminal complaints against these people. And his point was the Fed doesn't have the authority to charge people criminally, which is true, but he was head of the Federal Reserve. Now, if he said that, the question is, did he go to the Justice Department or the FBI to suggest that some of these people be investigated? Well, that's another question. Anyway, these are kind of ethics questions. So we've been talking about an engineer and how it involves complexity, ambiguity, uncertainty, and safety. And so today I want to talk a little bit about safety and safety factors. There's a guy who, Henry Petrosky, I think I mentioned him before, who wrote a book called To Engineer is Human, The Role of Failure in Successful Design. Petrosky is a civil engineer. I think he's retired now, living in Maine. But he was a civil engineer at Duke University, and he wrote a number of books. He wrote the book on the pencil, a whole book on the pencil. This was before he wrote Engineer is Human. Then the one on the paperclip, had a chapter on the paperclip. He's kind of a historian of things, but basically as he looked at things, and I don't know that he's the first person who ever came up with this, but he wrote a good book, particularly if you're a civil engineer, because that's where the examples come from, that we progress by failures, okay? To give you an example, the very first research contract ever given by the federal government was given in like 1836 to the Franklin Institute to try to figure out why the cast iron boilers in the river boats on the Ohio River, we hadn't gone past the Mississippi in 1836. We were still on this side of the Mississippi. But on the Ohio River, boats were blowing up and killing people, okay? And no one understood why. We didn't have fracture mechanics. We didn't know about toughness. We barely knew about strength of materials, okay, in 1836. So that was one of the first contracts, or was the first contract. Then, and I didn't bring a picture of it, I guess I could have. The thing that sort of helped precipitate the Boiler and Pressure Vessel Code, which is the American Society of Mechanical Engineers sells a code on telling you what you have to do, what are the rules if you're going to design and build a pressure vessel. Well, in 1836, we had boilers, okay, and this is the Boiler and Pressure Vessel Code, didn't come along until like 1905, I think was when they call it the beginnings of it. I don't think the first edition came out until 1916, but in 2005 they wanted to celebrate the 100th anniversary. So, but anyway, the Boiler and Pressure Vessel Code is about this thick. It comes out and gets renewed every 3 years, and there are supplements every 6 months. And for only $17,000, you can have a hard copy print, and I think for $16,000, you can have a digital version, okay? And it gives you all, for the 3 years, it gives you all the updates and stuff. And there are people who spend their life, yeah?
Well, I was about to ask, is there any one person who ever goes through the entire thing and knows and understands what's in the code?
Yes. There are some people who spend their entire life on that code. If you're designing nuclear reactors, okay, there's a pressure vessel there, and you better know how to do it.
So why don't the standards come with a guy who's already...
Oh, they do. I brought a smaller code with me. This is, since you asked the question, for welding, The boiler and pressure vessel code is one of the primary codes, but it only applies to boiler and pressure vessels. For bridges and buildings, you have the structural welding code, okay? For steel, they actually have it for aluminum and other things. But the first couple of hundred pages are actually the code, which tells you what you shall do, what you may do. And these do not have force of law until they've been adopted by some government agency. And then they do have force of law. This one has force of law virtually around the country for any bridge or building, because every state, every city that adopt, like New York City has their own set of codes, they'll write this into their codes. Say, if you're going to do welding, you must follow AWS D11. It turns out the federal government doesn't mandate safety for boilers and pressure vessels, but every one of the 50 states has adopted some part of the ASME code. But there are people, I mean, I have a good friend who's, well, he's probably in his 80s now, but for 30 years he was on the Boiler and Pressure Vessel Code main committee. There are probably close to 1,000 engineers who attend these meetings and help update the codes. And most of it's volunteer work. And it used to be, I could buy this in the 1990s for $200. Now it's $600 or $500, okay? Many of the societies have learned there's gold in them there are hills, because if you're going to be in business, the law requires you follow the code. And you have to follow the current edition of the code. And this one comes out every 3 years, okay? Just like the Boiler and Pressure Vessel Code. They tried a few years ago to bring the new one of these out every year, because you get a whole bunch of extra profit, right? But people yelled and screamed enough that they went back to every 3 years. But in any case, does that answer your question? There are people who really do it. There's no one who knows the whole tax code in the United States, okay? It's like 100,000 pages. But these codes, there are plenty of designers who can pick out exactly what's there. And if you want to get a certified welding engineer degree, or not degree, but certificate, you have to pick a code. You can pick any code you want among a group of 5 or 6, and they will examine you on that code, okay? That's part of the whole test. But part of the test is to show that you are familiar in some detail with the code. It takes hours and hours and hours to study these codes. They're not written to be conversational like reading a novel, okay? Yep.
So if they come out with a new version like every 3 years, I can't really imagine that like, the engineering will change that much on like...
Oh, it doesn't. It's just updated, okay? They updated with these committee meetings, and someone had some failure somewhere or some fight. And for example, I can look in this code, and this is common with a number of codes. Any new addition will be in underlines. So that paragraph didn't exist in the previous edition, okay? Well, the rest of these 2 pages, there's nothing underlined, okay? And even if it's only one word, they'll underline it. So someone who uses the code every day, they get a new version of the code, and they'll see the new stuff. Also, to finish answering your question, is there any commentary? Yeah, there's 200 pages here of the code, and then there's a commentary, which is about another 200 pages. And the commentary is written by the people who wrote the code, and it tells you, it interprets more than the code says directly. Here's the commentary. Bring it down. C 4.5. So they changed. You can see they changed the 5. The numbering changed. Okay, but it is a change. Okay, they added something. No, it looks like they took out 4.1. Okay, whatever 4. You could go back to the old code, and you'd see it had changed. So this one has a commentary that comes with it. The Boiler and Pressure Vessel Code, there are people who write books and sell them, okay, because they know the code in detail better than most people do, and it will help explain things. The codes are pretty dry reading, okay, so far as that goes. But they have force of law, and I actually have a module on codes and standards. And I mentioned once that I was teaching this to someone down at the what used to be the National Bureau of Standards. And she was head of, she was actually started at MIT as an undergraduate in physics. And of course, MIT won't admit their own undergraduates to graduate school. So she went to Harvard for her doctoral degree. And she was heading up like 100 or 150 people at NIST. And I mentioned to her I was teaching a course on codes and standards. She said, "You are?" She had never heard of anyone in academia teaching a course on codes and standards. I mean, I don't know. Well, do we have any civil engineers? We have one or two civil engineers in the course. But I never heard anything about codes and standards as a student. But you know, as an engineer, when I go out and do my consulting, I deal with codes and standards all the time. I mean, the last 2 days I was out in Calgary dealing with a problem of, you know, big steel transmission towers that have 500 kVA bringing electricity to the country and stuff. Well, one company in India sold 100,000 tons to build a bunch of these towers that are going to be in Alberta. If you figure it out, 100,000. There were 111 towers, and there's 100,000 tons. That means each one of these really big towers weighs 1,000 tons of steel, which is about $1.5 million just for the steel. And that means erecting one of these towers is probably $2 or $3 million per tower. So next time you're driving along the highway and you see these big towers, that's $2 or $3 million per tower, okay, for the really big ones. Anyway, and I was, you know, I had to go back through my knowledge of the code and help advise people on what the contract said we had to do and what it didn't say we had to do, because they were in a big fight of, did the buyer and seller were in a big fight about a $50 million fight. That's the value of their claims, to decide whether they carried out their contract properly. One of the things that I know well, because I've run across it many times, is section 6.6.5, just to give you an example, and I was quoting it yesterday. So there are sections in the code, and I showed you some before that talked about the responsibilities of an engineer. Here's contractor responsibilities, obligations of the contractors. Build it, okay? Visual, they're talking about inspection in here. This is section 6 is inspection. You got to inspect it, and then it points out there's some engineering judgment if there's faulty welding, okay? But really what I was getting to them is they're arguing over the inspection. People in India would do the inspection, and there would be people from Canada who were placed in the plant in India. Hey, you got $100 million worth of product. You often will put your own owner's inspector right in the facility. And if it's around the world and you have to send the inspector there to live there for 3 years, so be it. Okay, there are whole organizations that do that all the time. You've heard of some of them. You've heard of Lloyd's Register, which is, you used to know as Lloyd's of London. Lloyd's of London now is a bunch of insurance companies, but Lloyd's Register basically would put someone in a shipyard. This goes back hundreds of years. The owner would hire someone to be in the shipyard to look over the shoulder of the people building the ship. And we now have American Bureau of Shipping, Lloyd's Register, DNV, which is De Norske Veritas, and the French have Bureau Veritas, okay? And these are just quality control, quality assurance people looking over the shoulders of the people doing it to make sure they do a good quality job, okay? When you're buying $100 million worth of steel, you might as well have someone inspect it, right? But it says, if you ask for inspection that wasn't in the original contract agreement, you can have it. The contractor must give it to you, but you as the owner have to pay for it. You didn't put it in the purchase order to pay for it to begin with. It's an extra. And you're going to have to pay for it unless they can prove attempt to defraud or gross nonconformance. You're just doing a terrible job. You were careless and you didn't even care about being careful, or you're actually committing fraud. Those things happen, but in general, and so, there's a whole law that's built up around contracts and things because, look, if you've read about the government contracts, and this contract's over budget by 300%, right? The big dig was over by, 700% or something from the original estimate. And this leads to lots of disputes, okay? In fact, on the big dig, they brought me in, what was it? They had some hangers. They had some hangers in the tunnels. They were holding the roof up. This is before I was also involved in the one that collapsed and killed the woman. But this was before that, while they're still under construction. And some of the big steel bolts that were going to hold up the roof were supposed to be galvanized. They were supposed to coat them with zinc in a particular way. And the contractor had done it out of sequence. And the question was whether the threads on the bolts, these are big bolts, like 1.5 inches in diameter, whether they were going to rust in service. Well, these are all supposed to be hot dip galvanized, and hot dip galvanized, you just dunk it in a bath of molten zinc, and you get a pretty thick layer, like 2 or 3 thousandths of an inch. That's the guardrails along the highways and stuff. That's hot dipped. Or the paint buckets, not paint buckets, but the galvanized buckets that you on a farm, they just carry water or have a trough, and the cows and the pigs drink water out of the hot dip galvanized bucket. There's also electro-galvanized, and if I looked, a lot of this is aluminum, but if you saw any steel tubing, it's zinc plated. Well, that's 1/10 as thick, okay? So I was in this meeting, and this was going to bankrupt this little company that had made these bolts for the big dig. I mean, if they had to go in and undo, disinstall, this is what some of the engineers of the big dig were saying, and they said, we're going to make you uninstall all this stuff and redo it. And this little company was sort of a mom and pop company. They were going to go bankrupt under this. And so we had a little meeting, and I was hired to go in and kind of talk about whether this was going to really affect the corrosion up there in the roof, in the ceiling. And we were meeting with the chief engineer of the big dig. And the underling engineers, they were, we put it in the spec, and you need to do this, and you did it out of sequence, and blah, blah, blah. And so we go in the meeting, and I said, I've seen some of the construction. You got some electro-galvanized up there for the electrical stuff. And, I talked about the throwing power of zinc and how you have 10 times as much on hot dip galvanized, and the fact that they had a little area of 1/4 of an inch wide that didn't have some zinc on it. It would all be protected. There was plenty of zinc to protect it, because compared to the electro-galvanized, you had 10 times as much. Okay? And I said, if anything's going to start rusting up there, it would be the electro-galvanized, because it has less zinc. Okay? And I said, you're going to start seeing rust from the electro-galvanized a lot sooner than you're going to see it from these. And you can see all these engineers of the big dig. I said, oh, do you guys already have rust? They had to admit the electro-galvanized was already rusting. They hadn't even finished building it. Okay, we ended up coming up with a fix that wouldn't bankrupt the company. They didn't have to take everything down and everything else. We came up with a fix that would make the underling engineers happy, and basically the chief engineer was just sort of the arbiter between me and the guys who were trying to play hardball, and this is what the contract says. Well, there's always things that go wrong. And then an engineer, in fact, it says in the code, the engineer has to exert some judgment on whether it's important or not. You can have nonconformances, and then you can have waivers, or you can have new ways to fix it. In fact, that's what this $50 million dispute in Canada is all about. There were certain managers in Quebec who, we want exactly what we paid for, whether it was important or not. Okay, some things are cosmetic and hidden beneath, above the ceiling, which is basically what happened in the big dig. So this is where engineering's a lot different than just being a research scientist. At MIT, they teach you how to be a research scientist, right? as if that's what people do. 90% or 95% of the engineers are not what I call the wannabe scientists, but they're people who actually are going out trying to make something work and solve the problem and trying to decide when something goes wrong, what do you do about it? Okay? I used to work for a division of Johnson & Johnson, made medical instruments, and they'd have a manufacturing hiccup. And the question was, they come to me and they say, do we have to throw out all this $500,000 worth of parts we made, or can we do a fix? And I'd have to help them through and decide whether there was a fix or whether you had to throw it out. Sometimes I said, sorry, you got $500,000 worth of scrap. Sometimes I say, well, no, they can do this. You have to, but you have to get into the details. And you can't always write down equations for this, but you got to be able to justify it. And there's a number of times that I've been asked to go to Washington and talk to the regulatory agencies, in part because I'm at a university, I'm sort of a neutral party, okay, about these things. And sometimes there's a lot of money involved. I remember one day I didn't have to go to Washington because right up here by Burlington Mall, the Federal Aviation Administration has, they have offices around the country, but these offices have to approve parts manufacturing if it's not the original, well, that for everybody. If you want to sell an aircraft in the United States, unless you're going to limit it to flying it yourself or your family, you can, if you're flying it for yourself or your family, the regulations say you can build anything you want because it's okay for you to kill you or your family. But if you're going to sell it for other people to fly in it, you got to follow our rules. I'm not kidding, okay? There was once I'm really going far afield here, but there was once some people who wanted to be able to fly at Mach 2.5, same as like an F-14, okay? But first of all, the government wouldn't sell them an F-14, but also it would probably cost $70 million. Although some of these people, such as, well, it wasn't Harrison Ford, but some of these movie stars and stuff, they own their own helicopters. I mean, when I went through helicopter ground school, Harrison Ford had been there at Bell the week before learning how to fly his helicopter, okay? But there are some of these people who would like to fly at Mach 2.5. Well, you can design your own private aircraft, but the rules say you have to build half of it yourself. So they set up this factory in Reno, Nevada, and you could buy one of these for like $10 million, and you would have to come in and turn the screws and be able to say that you built half of it, even if you could, afford someone else to do it. The rules say you have to do it. So they were trying to qualify this, and this was basically an aerospace engine that they could buy from Pratt & Whitney or General Electric, and they kind of built an aluminum frame and put a seat in front. And then they had wings, okay? And they had lost their first test pilot over the Nevada desert, and I got a call at 6 o'clock one morning here at work, and this guy I know who's an accident investigator says, Tom, I want you to look at some parts I got. I said, sure, what do you want to come by? He says, I'm down here at the steps of 77 Mass Ave. I can be there in 5 minutes. I said, oh, okay. I'll meet you in 8140 or 8133. Anyway, I go down there. He shows me these parts where the owner of the company had died. He became the test pilot when the first test pilot died. And now he was dead, and his widow wanted to understand why her husband had died. Anyway, they got like $100 million. You had to put a $2 million down payment, even though this thing had not even been proven out, to buy this super duper plane that you could kill yourself in. And anyway, he brings by these parts, and I look at them. In about 15 minutes, said, there's nothing here. This is all overload failure. So tell me more about this accident. He said, well, they think they had wing flutter. They don't know exactly. He's at 40,000 feet. He's going Mach 2. And they think they had wing flutter, and if you get the wing flutter and it starts getting into an unstable mode, they think that maybe one of the lead weights on the end of the wing flaps had come off. So the wing flaps are the things that allow you to tilt and stuff. but one of the lead weights was there to dampen some of the vibration. And if that had come off, it would be asymmetric weight. It wouldn't be balanced, and they think that's what caused the wing to rip off. And the wreckage was spread out over 50 miles of the Nevada desert, okay? Because you're 40,000 feet going Mach 2. You know, the first parts that fall off land here, and, you know, the later parts land somewhere else. And so it was hard to get everything. I said, well, why don't you try to get me the end of the wings? Well, they brought in the two tips of the wings about 3 months later. And sure enough, they had adhesively bonded a 1 pound lead weight. And I could look at it. We didn't have the lead because it was gone. But I could look at the adhesive joint and say, oh, they didn't get enough adhesive here. And why they didn't put a screw in there to join the lead to the aluminum is beyond me. But to me, that was the probable cause. I mean, that was helped out by a aerodynamics guy. But I said, yeah, you got bad adhesive joint. Anyway, the whole company folded, and all the people put in their $2 million down payment. They lost it. These things go on all the time. There was a guy I know, he's passed away now, but actually no, it was another guy I know who actually bought into this too. And it was an all friction stir welded titanium skin plane, like a little Cessna, but it was, you know, it's going to be very light and stuff. And you had to pay $1 million down before the thing had even been designed. Okay, so there's lots of these little, well, I'd call them scams, but they wouldn't call them scams. Anyway, when you're doing these things, there's lots of uncertainties. And as Petrosky goes through and talks about the factor of safety, this is chapter 9, and you'll have it on Stellar, but it says safety in numbers. While engineers can learn from structural mistakes what not to do, they do not necessarily learn from successes how to do anything but repeat what they already did. And this is his thesis, that we learn from failures. You know, he uses the Tacoma Narrows Bridge and other things. And we have something called a factor of safety, where if we think the required load is going to be 100 pounds, we make it so it will support 150 pounds. That gives us a 1.5 factor of safety, 50% extra, because there's uncertainties out there in what we design. And so it turns out back in 1849, well, one of the things they can do, he talks about proof testing. If we want to have a rope that we're going to lift something, and we might need to lift 1,400 pounds, we might design a rope and test it at 3,000 pounds, and if it doesn't fail, we just prove that one rope will hold 3,000 pounds, and the chances of it failing when you load it again at 1,400 are pretty small. And proof load testing is done all the time. In fact, I kind of ran into that in the last 2 days out in Calgary. And you do careful inspections, but you need to know how to define failure. And it might seem, well, something fell, it broke. Well, that's a simple, but sometimes if you have a fatigue crack that gets to a certain size, then it has failed because you don't want to put it out there any longer. And that's what we do all the time on aircraft. We inspect them. We know what size cracks are acceptable. We do it in bridges and buildings. That's actually why I brought this thing. In this 200 pages, they're very explicit in chapter 6. It tells you if you're going to do ultrasonic testing, what size flaw you can accept. If you're going to find porosity, well, if you find one pore, that's easy. What happens if you find a cluster? And how close can they be in a cluster before you say, that's too much? The code has developed historically parameters that tell you this is acceptable, this is not, and if it's not, it's going to be classified as a defect. But just because you find an imperfection doesn't mean it's a defect. Okay? Now, in 1849, the Royal Commission in Britain asked a bunch of bridge designers how big safety factors should they have. Well, this is when they're designing bridges, if they designed a girder, they hadn't really worked out all the formulas like we have now, and they might just put the girder across two pieces and just load it up. with 10,000 pounds of something and see if it breaks. And they asked him, well, what type of safety factors should you use? And they asked some of the big names in the industry at the time, like Charles Fox, the engineer of the Crystal Palace, and other people. And they came up and they said, well, one of them said, well, I think 3. Another one said 7. The commission came up and said, well, we're going to use a safety factor of 6. So in 1850, we were using structural safety factors of 6. Now, you have to remember that is, we're using all kinds of materials. Steel that didn't have much toughness, cast iron that was very brittle just because inherently it's brittle. They talk about the Washington Monument. Well, that's a different topic I'll get to later. But it actually talks about the Washington Monument in crushing has a safety factor of 9. And that Washington Monument was designed in the 1870s. Okay. In any case, there are safety factors, and if you go look at the codes today, the factors of safety, bridges in the UK in 1850 had a safety factor of 6. The ASME Boiler and Pressure Vessel Code, which is one of the most sophisticated codes in the country, and includes nuclear reactors as Division 3 and things like that. For ductile iron, not gray iron, which is very brittle, ductile iron, which is almost as good as steel, you have to have a safety factor of 5 even today, because it's a casting, and castings can have big imperfections, whereas wrought materials, you've squeezed out the imperfections, and so steel, it might be a safety factor too. But the Boiler and Pressure Vessel Code, it's this thick, because when you design something, it will tell you what you have to do in the design and what's the factor of safety above your anticipated load, okay? The Structural Welding Code basically used to have 2 safety factors: dynamic loading, which is a bridge where you have trucks and buses and cars going over it and it vibrates, and that's 2.0. Anybody know why the Structural Welding Code would use 2.0 for dynamic or cyclical fatigue loading? It's because steel, actually, if you look at the old way of looking at stress concentration or at fatigue life, steel has something called a fatigue limit. This is not the way we look at it now. This is the way we looked at it 50, 60 years ago. But we had what we called an SN curve. S is stress, N is number of cycles, and actually it's log N. So it's 10,000, a million, okay, you're going in on a log scale. But you'll have a stress that would be your uniaxial tensile stress, and you come down, and I kind of went too far, but at about 50%, well, 50% would be down here, you get to the infinite life, okay? Steel under constant amplitude loading will have infinite life. If you have a lot of variable amplitude, it won't necessarily have variable life. But anyway, that's one of the reasons they use a factor of 2. Whereas on a static design, like a bridge building, there's not anything going over the building that's going to cause it to vibrate like a bridge. And so I have static, and the static design is 1.67, 5/3. Now, if I go through the old structural welding code from 15 years ago, they would require the welds to have twice 1.67 or 3.3 as a safety factor. Why? Because just like the castings in the cast iron, the welds can have porosity, they can have imperfections that are larger than you expect of the base metal. So the weld metal has to have twice the safety factor that you would have in the base metal. Okay, that's the way we used to do it, and we still do it sometimes. You can do it either way. OSHA, if someone's going to be up more than 6 feet in the air, OSHA, by law, requires 4.0 on the safety ladder. I go to the hardware store and buy a ladder, it will have a 4.0 safety factor. If it's rated for 225 pounds of person and tools on there, you can put 900 pounds on it. Okay? The odds of that failing are pretty slim, because a 4.0 safety factor is really big. Now, it turns out tree stands, hunters who want to go out and kill themselves, actually they want to kill something else, but sometimes they kill themselves. Tree stands are only a factor of 2. Okay? OSHA cares about scaffolding for construction, but OSHA doesn't regulate tree stands. It's sort of like build your own plane, kill yourself, knock yourself out. But if you're going to be doing it and you're going to have workmen building a building, you've got to have them with safety harnesses and things like that. In fact, I was watching on the construction of the Nano Lab. I kind of come up with an elevator there from the parking lot or parking garage, and they had a guy, and he was just a little bit more. He was like 7 feet off the ground, but he had a harness, he had a D-ring, and he had a cable. So if he fell, he wouldn't fall more than 6 feet. Why? Because they've learned if you weigh 200 pounds and you fall 6 feet, that's 1,200 foot-pounds. I did that calculation in my head, okay? And if you look at historically, when people fall, they can get fairly serious injuries when you have 1,200 foot-pounds. Okay, 1,200 foot-pounds is a lot of energy. The X-33 space plane started out with a 2.0 safety factor. They had some manufacturing problems. This was a $50 million structure, and they knew they had some big defects in it, so NASA sharpened their pencil and said, oh, we still got 5% safety factor above, okay? So they went and they tested it, and it actually passed until they started to warm it up, and the thermal stresses from going from liquid hydrogen temperatures to room temperatures, it failed because it didn't have enough safety factor, okay? But if it had been manufactured properly, it may not have failed, okay? I put in the New Orleans levees here about 1880. My great-grandfather worked, he was a civil engineer working on the levees. And I read somewhere after Katrina that the safety factor on the levees was 1.3. That 1.3 is one of the lowest safety factors I know of. Okay, typically safety factors are around 1.67 to 2. When it's like hoisting equipment above someone's head or someone more than 6 feet off the ground, they'll go to 4. Some cases when you're working with castings in a pressure vessel where the consequences of failure are pretty severe, blowing up a building or a city block, it's a safety factor of 5. Anybody have an idea of what the safety factors might be on a helicopter? No, it's actually very high. I was surprised. And actually, it's a trick question. I said safety factors. There's not one safety factor, okay? You're weight critical, and so they're going to look at how critical the failure would be. What was your answer? Okay. Most of the things I've seen are around 10, okay? Now, some things are not, and some things are critical, like the mast. There's no redundancy on the mast. If the mast cracks, you're going down, okay? And so I don't even know what the safety factor is. I suspect it might be something like 3. The problem is the mast is big steel, okay, it is heavy, and so they can't use a factor of 10. But most of the structural stuff, the spars, when I've done the safety factor calculations on these things, when I've had a failure, it's up around 10. But these are vibration machines. They sometimes call helicopters fatigue machines. So, and the consequences of failure is it's very easy to kill yourself, particularly if you lose your rotor. There's not much safety after that. If you actually still have the mast in the rotor, you can do an auto rotation. Anybody know what an auto rotation is? What's an auto rotation?
So you basically go into a controlled dive so that
Yep.
you spin up the kinetic energy in your rotor blades. And
Yep.
then
Yeah.
layer up at the last second and expel the energy and hopefully don't crash too hard into the ground.
So if your engine's working, you're spinning the blades, and that allows you to have lift. But if your engine quits working, you basically, if you have some forward momentum, if you're just hovering, you're dead, okay? But if you have some forward momentum, you can put those rotor discs, the rotor blades into the wind, your forward momentum, and the air coming through will cause them to freewheel, and they will give you some lift, okay? So I did an auto rotation once, and it's not much different than a regular landing if you have enough forward momentum. There's a little part of the envelope of height, forward velocity, where you can auto-rotate, and there's an area which is called the dead man zone, for obvious reason, where you can't auto-rotate. But helicopters are not as unsafe as you might think. I was surprised when I started doing some calculations. They they don't want, they have so many parts, and they're vibrating. They actually have quite an amazing safety factor for given the situation. So now what's happened in recent years, and that's what I brought these two books. The old way was called allowable stress design. We did that from the 1920s probably up through around 2000. And the first 9 editions of the American Institute of Steel Construction Manual of Steel Construction, and it's a really exciting manual. I think you need to own a couple of these books. I mean, one for home, one for work. You know, tables of what the sectional properties of an I-beam or a channel or something like that. But it also has some sections in here about design requirements. And what we did in the old days under ASD, allowable stress design, we basically said we're going to use 1.67 or 2.0. That's what the structural welding code used to say before 2000. Use AS, they didn't even call it ASD. You basically didn't know what the stresses were going to be. You're going to give 67% or 100% extra capability in your design, depending on whether it's dynamically or statically loaded. And you're going to, it doesn't matter if the stresses are coming from north, south, east, or west, top or bottom, you're going to just use the same safety factor. And historically, we found 1.6 statically loaded, 2.0 fatigue loaded was good enough, okay? We moved all the way down from 6 in 1850 to 150 years later, we were down to 2 or less. But then, in the 1950s, this engineer in the Soviet Union said, no, this doesn't make any sense. We're using too much material. And as an engineer, he wanted to do it better. He said, we can, if we know whether it's tension, compression, shear, bending, there are different types of loads. You can write down the stress tensor, okay, and you can find, you know, each one of those in the stress tensor. Rather than just assuming the loading can come from any direction, we often know what direction it's going to come from, and we can do a better design job. And he came up with what is load and resistance factor design. The AIC manual is now the Manual of Steel Construction. This one's in its 3rd edition. Actually, I think it's in the 5th edition. The 9th edition was the last ASD design. If I go to the 2010 welding code, it will say that I can use either allowable stress design there across the top or load resistance factor design, okay? And this has a safety factor of 1.67. This has a resistance factor. And you have to know a lot more about the loading on your structure. But if you know more about the loading on your structure, you can save about 1/3 of the weight. So there's a lot of money here, okay? If you're talking about these transmission towers out in Alberta, you're talking 100,000 tons, you know, you could be saving 30,000 tons, you know, you're talking tens of millions of dollars worth of material. Now, it turns out that there have been some interesting failures because of this stuff, and maybe since it's towards the end, I'm going to talk about on Tuesday. I mean, there are books now written. This is, you know, we'll look at some of the introduction of this. Steel structure design, ASD/LRFD, and this guy compares the two, and he shows that if you know more, but the problem is, that I'll talk to you about next week, is it's a more complex system. In general, you need to, most companies have proprietary computer programs to do the LRFD. ASD, we could all do on a sheet of paper with a pencil, okay? Well, actually, that's why we did it. Then they got to a point, the computers were doing that in the 1990s. But now, LRFD, it's just the American Society of Civil Engineers document 360 is a little too complex. This is where you have to ask, well, do you have to have some expert who really knows the whole thing? And the answer is, with LRFD, yes, you do. Or you have some computer program that tends to be a surrogate expert for them. because most engineers can't do it. I can't do LRFD, okay, on my own, okay? I haven't studied it. Some people coming out of school can, but most of them, unless they're doctoral level civil engineers, are going to be doing something that's sort of a, they're going to be using some canned program. And there's some interesting failures that come about because of canned programs, okay? So I'll talk about some of that. Okay, I'll see you next week. Have a good weekend.